to the chapter on introduction to micro machining. The organization of this lecture is as follows: introduction and classification of micro machining processes, the mechanical type of micro machining processes such as abrasive jet machining, ultrasonic machining, thermal micro machining processes such as electric discharge machining, electron beam machining, laser beam machining, electrochemical type of micro machining processes, introduction and classification of micro machining processes. We are in the 21st century, which is a competitive world. A country can be economic leader only when it is at forefront in research and developmental activities in the nation. From that point of view, microfabrication is going to witness excellence in research and developmental activities at a remarkable rate, as will be quite evident in this lecture and the following two lectures. Now, first let us understand what is fabrication or what is manufacturing or micro manufacturing later on. Building of machines, structures or process equipment by cutting, shaping and assembling components made from raw materials. From this fabrication point of view, you can classify these fabrication processes in macro fabrication, meso fabrication, micro fabrication and nano fabrication. This fabrication can be classified mainly in two classes, macro fabrication and micro fabrication. In place of four types of fabrication I have just mentioned, I am going to concentrate basically on macro fabrication in general, which also includes meso fabrication and micro fabrication, where I am going to take up some examples of nano manufacturing also. In macro fabrication means where the dimensions are large enough, you can see by naked eye, you can feel them by your hands also. Process of fabrication of structures that are measurable and observable by naked eye, they are visible by naked eye. Normally their dimensions are bigger than 1 millimeter. In case of micro fabrication, process of fabrication of miniature structures whose dimensions are comfortably mentioned in micrometers. For viewing them properly or observing them properly, you need microscopic equipments or microscopes for that particular purpose. Their dimensions are greater than 999 nanometer and smaller than or equal to 999 micrometer. Now, let us see what is micro manufacturing. We have seen four types of manufacturing: macro, meso, micro and nano. Now, let us just see what is the definition of micro manufacturing. A set of processes used to fabricate features, components or systems with dimensions most conveniently described in micrometers. We will keep this definition in mind while discussing the micro fabrication or micro manufacturing. Now, what this size comparison in micro manufacturing is very important to understand. Now, if we take the 100 micrometers, that includes the paper thickness which we normally use for writing, human hair which is around 100 micron size. If we take 8 micrometers, then red blood cells come in that category, capillaries also come in that category. 0.5 micrometers, they are visible light wavelength, machining tolerances also be nowadays talk many times in terms of half micron as the machining tolerances. 0.07 micrometers in the year 2010 or beyond, IC production design rules will be following or using 0.07 micrometers or 70 nanometers as their dimensions, and 0.0003 micrometers, that comes out to be 0.3 nanometer as atomic spacing in solids. That is 0.3 nanometer means 3 angstrom, and which is the spacing between atoms in the solids. Now, let us see here 6 feet tall man is 1.62 meters or 1.62 billion nanometer tall. So, you can convert this meter in terms of millimeter, micrometer, nanometer, and ant is 0.2 inch or 5 millimeter long. So, inches can be converted, and you can see the comparison between different species or human being or blood cells. Red blood cells are 2 to 5 micrometer wide. There are 5 million blood cells in a drop of blood. A standard DNA is of 1 to 12 nanometer wide. So, now you can just try to imagine what are these dimensions and how can you imagine them in your mind when we talk of all these dimensions. Now, here you can see a human hair is 60 to 120 micrometer depending upon the diameter or the thickness of the hair. Bacteria are 1 to 2 micrometer wide. So, in micro manufacturing, we should change a mindset of visualizing every product by naked eye, which is not possible. You have to take the help of high magnification microscopic equipment, just like optical microscope, scanning electron microscope or atomic force microscope, to view these products and see their structure, configuration, dimensions, shape, etc. Now, you can see here I have shown a scale length which starts with 1 centimeter to 1 angstrom. Influenza virus is 200 nanometer in diameter, but other viruses are smaller, as you can see here in the last figure. Now, the question is, every product that we see nowadays in our daily life, their sizes are reducing continuously. If you go back to 20 years and see your telephone, how big the telephone was, and today if you see the if you see the version of cellular phone, such a small cellular phone. Now, every much more features, much more better cell phones are available these days compared to what you had telephones. So, miniaturization or reduction in the size is taking place continuously, or you can see the case earlier we used to have the hard disk or magnetic tapes or other kind of the devices for storing the computer memory. Nowadays, if you see such a small chip is there or such a small pen drive is there, which can store as many as 14 GB data. So, miniaturization is continuously taking place in different areas of everyday life, and the question arises why this miniaturization is important. There are certain reasons for this. Minimizing, for example, minimizing energy and materials used in manufacturing. Certainly, this cell phone requires much smaller material for manufacturing as compared to our old days telephones. Same way, reduction of power budget, the total power consumption in these devices is much lower compared to the large sized devices. Devices are faster in response, increased selectivity and sensitivity of these devices compared to the older ones, improved accuracy, and they are more reliable compared to the large size. Definitely cost advantage is there, performance advantage are there, and integration with electronics and simplifying systems is there. Now, the question arises, what are the methods of micro fabrication? You have two categories of micro fabrication. One is by material deposition, another is by removal of the material. Either of the two can be used depending upon your device requirement or product requirement. There are various methods or processes which are used for micro fabrication using material deposition. One of them is electrochemical spark deposition, electro discharge deposition, chemical vapor deposition, physical vapor deposition, rapid prototyping, rapid tooling, LIGA. These are some of the material deposition processes. This is not the end, there are other processes also which have not been listed here. Then there are the various material removal processes. They can be classified in two categories. One is the traditional material removal processes, just like milling, turning, etc. And another is the advanced material removal processes such as ultrasonic machining, abrasive jet machining, electric discharge machining, electrochemical machining, etc. Now, micro products. Nowadays, focus is on miniaturization through development of novel production concepts, especially micro and nano for the processing of non-ceramic materials. Micro fabrication deals with all kind of manufacturing processes, but at micro and nano levels. That means, their features or their dimensions can be expressed in terms of micrometer or nanometer. The replication of micro parts through molding is one of the preferred routes for micro manufacturing because of its mass production capability and relatively low cost. Although I am not going to discuss micro parts production through molding process, but this process is the unique process or unique concept which already prevails for macro parts. Same has to be used for micro parts if mass production is to be done. Mass production you cannot do economically and at a faster rate by material removal processes or even material deposition processes. However, in this talk I will mainly concentrate on micro atreseous processes, that is micro machining processes. These processes also have their own importance for making the dies for molding purposes, micro molding purposes or punches or other kind of the tools and toolings. You have to go for atreseous processes, that is micro machining processes, that I am going to deal today and in the following lecture. Material removal processes, again there are two categories: micro nano machining processes, micro nano finishing processes. Now, there is a basic difference in micro nano machining and micro nano finishing processes. In machining processes, we are making micro features or micro components giving proper shape and size, while in case of finishing processes we are improving the surface quality of a macro or micro products, but that surface finish or surface qualities are at micro or nano level. Now, micro nano machining, there are two types again: traditional machining processes and advanced machining processes. In case of micro nano finishing also, you have traditional finishing processes and advanced finishing processes. Now, micro machining is made of two words, micro plus machining. We already know the definition of micro, that is 10 raised to power minus 6 meter, and machining we all know about what the machining is, that is the removal of the material at micro level. Now, macro components, but material removal is at micro nano level. This is very important to understand. When we talk of micro machining, it does not always mean that you are going to make micro components. The component may be of the macro size or meso size, and you are creating the features of micro size or nano size. So, macro components, but material removal is at micro nano levels. That material removal is in the form of chips if it is being machined by applying the mechanical forces, or you can get the debris of a very small size if you are using the thermal processes like micro electric discharge machining, laser beam micro machining, or you will get the reaction products in case of electrochemical micro machining. Second one, micro nano components and material removal is at micro nano level. This is very simple, that you are when you are going to make MEMS, names etc., the components itself or the elements of the device itself are having the dimensions of micro size, then definitely the material removal from those devices or parts or elements is also going to be at micro or nano level. You can see a very interesting example here. Here is a 2 millimeter by 2 millimeter size frame, which is having so many components you can see, and you can measure now the dimensions of these components. And here I have tried to show a leg of a house fly. Now, such a small leg a house fly has. Now, within that size you can see how many components are there. So, that gives you an idea what size of components we are talking about when we talk of micro parts or micro components. Unfortunately, the present day notion is, when we talk of micro machining, normally it comes in the mind of the people that machining of highly miniature components with miniature features. Literally it should not be so, it is not correct, because we are talking of machining at micro level, not making the component at micro level. So, more correct definition of micro machining is material removal at micro nano level with no constraint on the size of the component. Component can be either macro component, meso component, or micro component or nano component. So, micro machining, let us see what are the various processes in traditional micro machining processes: micro turning, micro milling, micro drilling, and so many other traditional micro machining processes are there. Then there is a whole list of advanced micro machining processes like micro EDM, micro ECM, micro AJM, laser beam machining, electron beam machining. All of them come into category of micro machining, including ultrasonic micro machining. If you want to classify micro machining processes, I have shown here, you can see whatever I have mentioned earlier slide, you can see there is a classification. There are a class of traditional micro machining processes, micro milling, micro turning, micro drilling, micro grinding, etc. Then there is a class of advanced micro machining processes. Mechanical type advanced micro machining processes include ultrasonic micro machining, abrasive water jet micro cutting, micro abrasive flow finishing, micro magnetic abrasive finishing, micro magnetorheological abrasive flow finishing, micro magnetic float polishing, and this is MFP, not MPF. Then on the thermal side you have laser beam micro machining, electron beam micro machining, plasma arc micro machining, and other processes are also there which I have not listed here. Then in the third category, if you see chemical and electrochemical, which includes electrochemical micro machining and photochemical micro machining. These are not the complete list, you can add many more processes to this particular list. Now, there is another category that is known as hybrid processes. Now, if you take one single process which has many merits and some demerits also, but if you combine a particular process with another traditional or advanced machining processes, you may overcome some of the disadvantages of a particular process. And if you combine two or more than two processes and try to make use of the merits of these processes, then you call it as a hybrid process. So, you have certain categories here like electrochemical spark micro machining. Here you have ECM process combined with EDM process, and you are using it for machining of material at micro nano level, then you call it as electrochemical spark micro machining. Same way electrochemical micro grinding, ECM process we know it is applicable for electrically conducting material, but surface finish obtained is not that very good. And we also know grinding process, here material removal rate is quite low, but surface finish obtained is controllable and quite good compared to ECM. So, if you combine these two processes and use it for micro level feature creation or machining or finishing, then you call it as electrochemical micro grinding. Same way electric discharge micro grinding, where EDM and grinding processes are combined together to take advantage of both the processes. Then another process you have electrolytic in process dressing, ELID, and other processes are also there. They come under the category of hybrid processes. Some of them I will be discussing. Now, let us see very interesting some couple of examples of micro parts. Now, you can see some micro machine part. Here you see this particular interesting part, if you see it carefully, it is laser cut stain like pattern in miniature stainless steel tube with 1.25 outer diameter. You can see here the outer diameter is 1.25, but in this is hollow from inside and different features are created which are of micron size, and it is not that easy, it is very difficult to make this kind of component. Then here you can see another simple, not that complicated, but it is laser drilled hole of 15 micron size pattern in polyurethane tube. So, this is the tube you can see here, and these are the different types of the hole, large size and small size, that have been created using the laser beam. Now, I have mentioned to you that we have traditional mechanical micro machining processes. Here M is missing, AMI micro machining. Now, there are certain problems associated with mechanical type of micro machining processes that are shown here. Mechanical deformation takes place when we are talking of micro features or micro nano patterns, then mechanical deformation becomes very important. Even a slightly larger force will deform or damage the feature. Thermal deformation, because any mechanical machining process you take, heat is always generated, and because of that heat the deformation of the machine features or component may take place, which will change the shape and size of the component. Surface integrity is another problem. Then gap between tool and workpiece, I will show you the figure for this in this slide itself, and coordinate shift in tool handling. Now, you see the example here, if you are making the tool at a particular machine and using this particular tool on another machine, it really becomes a big problem. You can see here, if you here in this particular case you are making the tool on a machine, and on the same machine without disturbing the tool you are making the part, then it works nicely, because axis of the tool, axis of the workpiece, axis of the machine itself, they remain intact, there is no change. If you are shifting it, then this kind of the problem may arise, like off centering, one axis is here, another axis is here, and this will damage your component, or you will not be able to get the right kind of components, or there may be some tilting of the tool compared to the axis of the workpiece or the machine. Again you are not going to get a correct kind of the machine features or the component. Tool and spindle handle as a set, if you are handling both of them together, but still there may be a shift of the axis, that also is going to create a problem. So, one has to be very careful while doing mechanical traditional type of micro machining operation. Now, these are the very important components which I have taken from certain site mentioned here. Now, you see here in the left side, this is a world's smallest steam engine. The pistons are 5 micron in size. You can see here the pistons are inside this, and they are 5 micron in size, and it actually works. This is not just a model, it really works. They operate it. Now, on that side you can see here micro clutch mechanism, gears are 50 micron size. You can see the different parts over here, and they move with respect to each other, and they work, really they deliver the work. Now, here is another example. You can see the matchstick head over there, and compare the dimensions and the sizes of these different components that are shown here. So, this really gives you an idea that you should change your mindset as long as visualization of micro and nano features and components are concerned. Now, some more capabilities of micro machining. You can see here example micro end mill, tungsten carbide 100 microns diameter in this particular case. Now, you can see here 2.54 micron size smallest electrode that has been created over here, that you can see on this size, and this is the size of the hair. Here internal, here another example on this side, micro holes diameter 13 micron, they are shown over here with the arrow, you cannot see it clearly, material is platinum. Now, microfluidic channels, they are commonly used, and they are made here on stainless steel sheets. Here is the gripper for micro assembly, semiconductive, not really a gripper, it is just a hole over here. So, it is not gripper, and you can see here internal micro gear, how beautifully and sharply it has been made, and they have been taken from the site. Now, let us see advanced micro machining processes. Principles in general we have already discussed while discussing individual advanced machining processes. Still I will show you in very brief and quickly, I will explain the principles also. Let us see advanced micro machining processes. They can be classified as mechanical micro machining, thermal micro machining, electrochemical micro machining processes, and finally chemical micro machining processes. Though these are the basic 4 categories of micro machining using advanced machining processes. Let us see the examples of advanced mechanical type micro machining processes, which includes abrasive jet micro machining, abrasive water jet micro machining, ultrasonic micro machining. Now, since principles we have already discussed while discussing these individual processes, so I will just give you some differences between macro and micro machining and some peculiar examples of the application of these micro machine parts or micro machining processes. Please note here very carefully that while discussing these various processes, I am not going to discuss the working principle. Now, if you see here, abrasive water jet machining principle is shown over here. Now, it is simple, you have the water inlet over here, abrasive is being fed from the side, and here is the mixing tube in which water and abrasive particles mix with each other, and then abrasive water jet is coming out over here. Now, the important point to note here is that you will get micro machining or micro machine parts when the nozzle size is really very small, otherwise rest of the things remain same. Now, while applying macro machining processes for micro, you have to scale down the machining parameters, just like in this particular case nozzle diameter has to be reduced, pressures have to be reduced, and more importantly the size of the abrasive particle have to be significantly reduced, because when we talk of micro machining, the size of the abrasive particle should be very low, maybe few microns or sub micron size of the abrasive particle, then only you are going to get the clear cut features. As you can see over here that the width of the kerf is quite small. Here is the abrasive water jet cutting, and here is the abrasive water jet coming out of the workpiece after cutting a slit in the workpiece. Working principles remain the same, that the kinetic energy of the abrasive particles and water jet are utilized for removal of the material from the components. In case of ultrasonic micro machining, again the abrasive particle size goes significantly low, as well as the size of the tool also has to be in terms of micron size, then only you will be able to drill the hole or create the features of micron size. Rest of the principle remain the same, except that here the frequency of vibration is very high in terms of megahertz rather than kilohertz, and you can see here the feature created is just the cavity with the help of the tool over here, and this is the tool holder which is vibrating at megahertz frequency. In case of abrasive jet machining, again you can create the features of micron size using the same principle, that is the air is the carrier and abrasive particles of micron or submicrons of very low size, that is few microns or few say less than 100 micron size, and you will be able to create the cavity. Working principle remain the same, which I have already discussed. The principle remains the same in case of all these three processes. If abrasive particle is hitting a hard material, brittle material, then fracture is going to take place, brittle fracture is going to take place, and very tiny chips or fracture debris you are going to get out of it, depending upon what is the size of the abrasive particles and what are the properties of the workpiece material and what is the kinetic energy with which abrasive particle is hitting the workpiece. Now, if it is a ductile material, then in place of fracture you may get the deformation of the workpiece depending upon at what angle an abrasive particle is hitting the workpiece. As you can see in this particular figure, by shear deformation it is removing the material in the form of the microchips. So, the forces acting on each particle and particle size will decide the scale of material removed, whether it is macro, micro or nano size. Now, let us see some examples of abrasive jet micro machined parts. You can see here cross sectional profiles of typical masked PMMA channels. It is in one pass, you can see the size and shape of the micro machine channel, and in 11 passes you get the depth to the machine channel, and you can compare the dimensions because the scale of 200 micron is given here. So, it clearly indicates the capabilities of abrasive jet micro machining process for creating the features of the micron size. Working principle and setup for ultrasonic micro machining remains the same, which I have already discussed. You can see over here, shown over there, that is the horn is there, tool is there, dielectric fluid is there. Now, here this particular setup indicates the ultrasonic assisted EDM process, because EDM control system is there and workpiece is electrically conducting, that is shown over there, tool is shown over there. Ultrasonic vibration, when combined with a favorable abrasive slurry USM, creates desired accurate cavities of any shape through the impact of fine grains. The machining process is non-thermal, non-chemical, non-electrical, and thus produces high quality surface finish. Application you can see here, amplitude of vibration 5 micron, workpiece material is silicon, tool material tungsten, tool size 50, 100, 150 micron, abrasive grain size type is polycrystalline diamond powder, size of abrasive grain is 1 to 3 micron. So, you can see the size of the abrasive particle that you require, very small, and total tool feed rate 515 micron. Now, this is the cavity, you can see how fine you have obtained the cavity, and here is the scale shown over there, and USM generated micro hole drilling diameter is 66 millimeter. So, it is basically only by ultrasonic machining, not ultrasonic assisted electric discharge machining, which I showed to you in the earlier slide. So, and here is the silicon, which is normally very difficult to machine with such fine features. Now, this is another important very good application. You can see vibration is 39.5 kilohertz, vibration amplitude is 3 microns, again silicon workpiece, tool material is tungsten, and tool size is 50 micron, and abrasive grain type is polycrystalline PCD powder, abrasive size is still smaller, that is 0.5 to 1 micron size, and tool wear ratio is 0.12, and gap is about 6 micron. Now, you can see here the projection that has been created over here and the milling that has been done over here. So, such kind of complex features also can be machined with the help of ultrasonic machining process. Here is the reference. Now, there are certain advantages of ultrasonic micro machining over the other processes. Machining any materials regardless of their conductivity. This is very important advantage, because ultrasonic machining does not require electrical conductivity of the workpiece to be machined, or it need not be magnetic material or high thermal conductivity or low thermal conductivity are also not the consideration for this particular process. Ultrasonic machining apply to machining semiconductor such as silicon, germanium, etc. Ultrasonic machining is suitable to precise machining of brittle materials, which is difficult by other processes, because brittle fracture probability is always there. It can drill circular or non-circular holes or cavities in very hard materials, as we have seen 2 examples in the last 2 slides. Less stress because of its non-thermal characteristics, and secondly, the amount of material removed by each abrasive particle is very small, because the particle size itself is of 1 to 5 or 1 to 10 micron. So, the total force acting is also very small. However, there are certain disadvantages of ultrasonic micromachining process. Ultrasonic micromachining has low material removal rate, that is the process is very slow compared to other processes. Tool wear fast in ultrasonic micromachining. Machining area and depth is restrained in ultrasonic machining, because depending upon the size of the tool you can remove the material from the workpiece. Now, this figures I have already shown, I just want to show this particular part, that when you are machining with the help of abrasive water jet machining, and if it is a deep machining or deep cavity creation or deep cutting, then surfaces that you are going to get will have different characteristics at different depth. Now, you can see also at different feed rates. If feed rates are different, the characteristics of the machined surface will be different. If depth is different, then also the characteristics of the machined surface are going to be different. So, you can see here at low feed rate the kind of surface you are getting, at medium feed rate and at the high feed rate large number of striations are observed, which are really not desirable. Now, let us see some specific applications or examples of the advanced thermal micromachining processes. We will see the electric discharge micromachining process examples of the components. Then there are a set of beam micromachining processes like laser beam micromachining processes, electron beam micromachining processes and ion beam micromachining processes. I will just give few examples of the parts fabricated using these processes. However, ion beam micromachining process really is not a thermal process, it is not a thermal process, it is non-thermal process. However, it has been placed in the category of thermal micromachining processes as being done by various other authors and researchers also. Now, let us try to understand the working principle of ion beam machining process. As you can see here, as the ion comes and hits the workpiece surface at the top, it has the energy, it has the single ion is supposed to remove the material from the top surface of the workpiece in the form of atoms. The energy of each ion should be just sufficient to remove one atom, but normally the energy of each ion is more than the required one for removal of the single atom. That is why one single ion removes many atoms at a time, and if the energy is high enough, then what it will do? It will go sit inside the surface, that is in the subsurface, and get planted, and if it happens, then really it is damaging the workpiece surface, which is not desirable. So, you can see here various features are there of the setup, and here ion beam is scanned over the surface, where from it is removing the material in the form of the atoms. Now, here is the working principle of the electron beam machining, which we have already discussed, and again here localized heating by focused electron beam, gradual formation of the hole as you can see here compared to this one, and here penetration till the auxiliary support, this is the auxiliary support, this is the workpiece to be machined, and then removal due to high vapor pressure, because this auxiliary support creates the vapors, and these due to these vapors when they try to come out of the hole, they remove the molten material of the workpiece, and that is how you are able to eject the remaining molten material from the cavity or the hole in case of electron beam machining. Then laser beam machining is very interesting process, and there are two types of lasers, one is the continuous wave laser and second is the pulsed wave laser. Both have merits and demerits. Now, I need not to explain this, we have discussed it. Now, this is important figure, you can see here there are various kind of problems if you have a long pulsed laser. Now, you can see various defects are shown over here, these are the sir, recast layer is here, and then you can see here micro cracks are generated over here, heat affected zone is there, and then you can see damage to the surface, over subsurface damages are there. Now, all these defects are there if you are using long pulse laser beam machining process. If it is a short pulse laser machining process, you can see here all those defects which are shown over here, they are absent over there. There is no surface debris over here, as you can see, no micro cracks are there, no shock wave is there, no melt zone is there. This is the hole which has been created over here, and no heat transfer to the surrounding material is shown over here, and no damage caused to the adjacent structure, that is the adjacent structure. In this particular case, the adjacent structure has been damaged, as you can clearly see over here, but in this particular case there is no damage to the adjacent structure. So, it is always desirable that you use short pulse laser micro machining setup if you want highly accurate and well designed component as such. Now, let us see the example of electro discharge micro machining. Now, we all know the working principle of electro discharge micro machining, that there is a tool which is normally cathode and there is a workpiece which is normally anode. So, the workpiece material should be electrically conducting. In EDMM, material is removed by the thermal erosive action of electrical discharges or sparks provided by the use of a pulse generator. Now, the same principle of EDM is applied to remove material at micron level for micro machining, and you can see the setup over here, the same type of setup is there also. In micro EDM, the key is to limit the energy in the discharge. This is very important, because you are scaling down the macro EDM process to micro EDM process. So, in each pulse the total energy contained should be very low compared to macro EDM, otherwise the part itself is burn out and get damaged. The working principle we have already seen. When sparking takes place between the tool and the workpiece in electric discharge micro machining, also sparking takes place between the tool and the workpiece, and you can clearly see that material is removed from the tool as well as from the workpiece. In case of macro, these cavity form are much larger as compared to the micro EDMM, and definitely the voltage that you are using is very low compared to the voltage that you use in case of macro EDM. Now, this is the figure related to the macro EDM, where 100 micron size of the plasma column, 100 micron size at the width of the ionized column is shown, but in case of EDMM, electric discharge micro machining, this column is very small, maybe within tens of microns or even less than that, depending upon various micro machining parameters. So, here it shows the comparison of the EDM, that is macro EDM and micro EDM. You can see mechanics of material removal in both the cases remains the same, that is melting and evaporation aided by cavitation. Material removal rate are very different. In case of EDM, this is 3 into 10 raised to power 5 micrometer cube per hour, while in case of micro EDM it is 0.6 to 6 cubic millimeter per hour. So, there is a vast difference in the machining rate. Dimensional accuracy is 10 to 15 to 50 micrometer in case of EDM, while in case of sinking EDM, but micro EDM you have as good as 3 micrometer and 1 micrometer in case of wire EDM, that is wire electric discharge micro machining. Surface finish in case of macro EDM is 0.2 to 2.5 micrometer, while in case of micro EDM it is 0.4 to 0.5 micrometer. Tool material that can be machined are more or less the same in both cases: copper, brass, copper, tungsten alloy, silver, tungsten alloy, graphite, etc. While in case of micro EDM, tungsten electrodes up to 0.1 millimeter diameter, that is 100 microns, smaller, sharpened in the machine up to 20 micron, and they are used as the tool. Gap maintained between the tool and the workpiece in EDM is 10 to 125 micrometer, while in case of micro EDM it is much smaller than this particular value. Now, you can see the examples of electric discharge micro machining process. Now, if you see here microfluidic mixtures, this is shown over here, and the enlarged view of the same is shown here. Now, you can see these are the different channels, etc., obstructions given over here, and this is the microfluidic mixture that has been created using micro EDM process. Now, here is the 520 micrometer diameter extrusion die that has been created using electric discharge micro machining, and here is the ladder with 100 micrometer gap between teeth. You can see over here they have been made, and you can see this is the hole of 65 micrometer pin over molding jig that has been made, and these are the micro gears whose diameter is 520 micrometer. So, you can use this process EDM process for making micro features as well as micro components. This is very clear from this particular slide. Other examples of electric discharge micro machining, you can see here that here is a kind of the tool they have made of 6 micron diameter size, which can be used for electrochemical process or EDM, micro EDM process or micro ECM process or ultrasonic micro machining process or any other kind of the processes. You can use these kind of the tool. Now, you can see here 68 micron wide slots drilled with 50 micron electrodes, and this is the 32 micron diameter hole drilled with 6 micron electrode. So, you can see there are the differences in the size of the tool and the difference in the size of the machine feature. Now, let us see some interesting examples of electron beam micro machining. This I have already explained, I am not going to discuss it in detail, except that you are getting a beam of the electrons which is focused and controlled by certain devices, and this beam of the electron hits the workpiece surface, and these electrons are having very minimal mass, but the velocity with which they are moving towards the workpiece is very close to the velocity of the light. That is why the kinetic energy of these electrons is so high that they are able to create very high temperature in the localized area, and that temperature is so high that the material which is to be machined can melt and even vaporize it.